today we partially prove this theorem. Let R be a Dedekind domain. And let I be any ideal in the ring. Then I can be uniquely written as a product of prime ideals. I will not give you the complete proof of this because that requires, it's not very difficult, but it requires some effort. So I want you to make that effort on your own. So instead what I'll do is I'll give a partial proof and leave the rest to you. So the key property that we are going to make use of is the following. This is the property I am going to make use of. I will not prove this property. It's a very interesting statement. It says that if you have any ideal I in a Dedekind domain, then there exists another ideal J in the ring such that I times J is a principal ideal. So let's assume this to be true and proceed with the proof. Okay. One very interesting consequence of this is the following. In fact, I'll show you two consequences. The first one is cancellation. That if two products I1 and I2 are equal, and these are, of course, all three are ideals, then I1 equals I2. Essentially, it says that I can cancel I from both sides of the equation with exactly the same way as we can cancel numbers. This is not at all obvious, but by using the property above, we can make sure of that. How? Well, if you have I1 equals I2, and corresponding to ideal I, we have an ideal J, such that I times J is a principal ideal. So I1 equals I2 implies I1 equals I2. Okay. This implies Ji is principal ideal AI1 equals principal ideal AI2. Okay. And this implies I1 equals I2, because you can easily cancel principal ideal multiplication. Why? Take any element B of I1, then AB of I1 is in A times I2? Okay, let's see that. Okay, fine. Let me write it with another different ink. Correct? Okay. Now a Dedekind domain has the property that if it is an integral domain, which is that if A times C is 0, then either A is 0 or C is 0. In this case, A is surely not 0. This is, of course, follows from this fact. And so B minus B prime is 0. So this shows that B prime, whatever is in I1 is in I2. B was in I2 and B is in, sorry, B was in I1 and B therefore is in I2 also, and vice versa. So it shows that I1 equals. So that's the first interesting consequence. The second one is that if I is contained in I dash, then if ideal I is contained in ideal I dash, then I actually can be written as a product of I dash with another ideal J dash. See, the converse of this is always hold. We have seen that if I is a product of two ideals, then I is contained in both the ideals. In fact, I is contained in the intersection of these two ideals. This we saw a long time ago. This shows the converse, that in case I R is a Dedekind domain, then containment is sufficient to imply that I can be factorized as I dash times something. How does this work? So let's start with this, that we have I times J is a principal ideal. No, in fact, we should use the J corresponding to I dash. So I dash times J is a principal ideal. So let now this requires some explanation, but before that let me see if this is working out. Yeah, I think it does. So I dash J is a principal ideal generated by A, and now I'm defining J dash to be I times J divided by A, and I need to explain that. See, I is contained in I dash. Since I dash times J is a principal equals principal ideal generated by A, this is another way of saying that all elements of I dash J are multiples of A. So since I is contained in I dash, all elements of Ij are also multiples of A. And 1 by A simply means I just divide all those elements by A. So the elements in here are multiples of A, so just cancel out or take out A from this, and you get elements of Ij divided by A. I'm not saying that these are A is invertible. I'm simply saying that if A times B is in Ij, then B is in J dash. So this is defined as set of all B such that AB is in Ij. And since we know that every element of Ij is of the form A times B, so this definition makes sense. J dash is an ideal, because if B1 and B2 are in J dash, then B1 plus B2 B1, B2 in J dash means A B1, A B2 is in Ij. This implies that since Ij is an ideal, A B1 plus B2 is in Ij, and this implies that B1 plus B2 is in J dash. And similarly, if you have B is in J dash, then AB is in Ij implies any time CAB is also in Ij, this being the Ij being an ideal, this implies that CB is in J dash. So that shows that J dash is. So J dash is an ideal of R. And now let's look at what is I dash times J dash. What is this equal to? Is I dash times 1 by A Ij. Is this? Okay. Just rearranging because this is commutative multiplication. I dash J by definition is this. What is 1 by A times principal ideal A? This has all multiples of A. Sorry? Is R itself, or this is just 1, principal ideal 1. And any ideal times principal ideal 1 is just I. So this shows that I factors as I dash times J dash. The two very interesting properties follow by that result. And we'll make use of both of these. Okay. So now let's consider I and R, which is an arbitrary ideal in the Dedekind domain. Okay. First, I will show that I is a product of prime ideals. Let's assume for the sake of contradiction that it is not. Okay. In fact, I'll say that let's collect all ideals of R which are not products of prime ideals, and let this collection be the script M. I'm going to show that this collection is empty, and that will prove the lemma. Okay. Well, since our assumption is that it is M is not I is not a product of prime ideal, then M is not empty. Clearly, because I is in M. Now consider a maximal element in M. That is, start with I. See if this collection M has an ideal which is a superset of I. And keep taking larger and larger sets containing the previous ideal, larger and larger ideal. And by the fact that the ring is Noetherian, one of the consequence of that is that any such chain of increasing ideals is going to be finite. Because you can realize that quickly, because all ideals are finitely generated. when you look at an increasing chain of ideals, you are basically saying that you are increasing the number of generators essentially one by one. And so since there are only finitely many generators in the ideal, total any ideal is only finitely generated, so there won't be many or only finitely many ideals in this chain. That's a bit of a intuitive proof, not a formal proof, but you can formalize it along these lines. So consider an increasing chain of ideals. Which starts with I contained in I1, contained in I2, IL. And IL being the maximal in this chain. So any ideal that strictly contains IL is outside. Now IL cannot be not a maximal ideal of R. IL is maximal in the chain. There is no ideal bigger than IL in this chain. But if you look at the ideal IL, it is not a maximal ideal in the ring R. Because of the property we proved that every maximal ideal is prime. So if an ideal is a prime ideal, then of course it can be written as a product of prime ideals. So IL cannot be maximal. So let's say let J be a maximal ideal containing IL. Fine. So J contains IL. Now invoke the property number 2 which is just showed. That means that IL can be written as J times some J dash, okay, where J dash and J both, of course J contains IL, J dash will also contain IL. Yes? Can J dash be equal to IL? Then 1 times IL equals J times IL. J dash being equal to IL, and IL equal to J dash IL. This implies, oh, this is non-trivial, of course. Why? Oh, because of the cancellation. Of course, yes. J is a maximal ideal by definition is non-trivial in the sense it is not equal to the full ideal. Then by cancellation, J equal to 1, not possible. Okay. Therefore, J dash is not equal to IL. So IL is strictly contained in J dash, and IL equals J times J dash. Now J is a prime ideal in itself. J dash is a strictly larger ideal than IL. So it is not in M, which means J dash can be written as a product of prime ideals, which means IL can also be written as a product of prime ideals. All the prime ideals of J dash times J, which is a prime ideal. That's a clever proof. and this is a contradiction. So that's the proof of the lemma, which shows that every ideal can be written as a product of prime ideals. And now we need to show that this expression is unique. And that's also now will follow pretty simply, which is that let's say I1, I2, dot 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 I k be equal to J1, J2, JL for so let's consider two products of prime ideals which are equal. This implies that I1 contains this product. So I1 is a prime ideal and it contains a product of prime ideals. What would this imply? I claim this implies that I1 equals one of these JIs. Suppose JT, okay, is not a subset of I1 for 1 less than equal to T less than equal to L. This implies that there exists AT in JT minus I1. Okay, I should use the correct symbol here. So if JT is not in I1, then there is an element of JT which is not in I1. Okay, but this product A1, A2 to AT is in I1. Now I1 is a prime ideal. What is the property of a prime ideal? By definition, an ideal is a prime if whenever AB is in the ideal, one of A or B is in the ideal. So if this product A1 to AT is in the ideal, one of not AT, it is A L. One of ATs must be in I1, and that shows that whichever, this assumption that none of the JTs are contained in I1 was wrong. So what we have managed to show after this is that if a prime ideal I1 contains a product of prime ideals, then this prime ideal is actually contains one of those prime ideals itself, not just a product, but one of the prime ideals itself. Now JT is also a prime ideal. I1 is a prime ideal and JT is contained in I1. Now we use another property of Dedekind domains, which is that those conditions that I listed for Dedekind domains imply that every prime ideal is maximal. In fact, the three definitions of prime ideals that I gave, I think I mentioned this last time. The three definitions of prime ideal I gave earlier, all of three coincide for Dedekind domains. So every prime ideal in particular is maximal. JT is a prime ideal, and which is contained in ideal I1, which is also a prime ideal. So JT has to be maximal I1 also has to be maximal, which means Jt is equal to I1. And now go back to the product. So we have now from this reasoning, what we learn is that I1 occurs on the right hand side also. And now I can renumber or rearrange right hand side so that Jt is J1. Now use the cancellation property. This implies that I2 to Ik is equal to J2 to Jl. And repeat. So you just keep cancelling the identical ideals from both sides, and eventually we get that firstly L equals K and Jt equals It. Good. So this gives you a flavor of the arguments that one can use working with this abstract ideals. The key thing, I mean, I showed you the entire proof except this key lemma. Where was that? For every ideal I, there is an ideal J such that Ij is a principal ideal. This really provides the heart of the proof. And the proof of this is a little tricky, but completely elementary. That is, you can follow it from the concepts you know. So try to think about it. Any questions on this? This is probably the longest proof I have done in this course. And quite abstract also. It seems like this manipulation of symbols without much intuition. If you think about it, you will find there is a clear intuition that basic one is trying to use the, just cancellation is a very powerful tool of so which we can use to prove the uniqueness, and the containment being equivalent to factorization. We use to show that there exists a prime factorization of every idea. Any questions? So this is a story of the development by Kumar and then Dedekind. So after significant amount of effort, which I just outlined earlier, they were able to restore this unique factorization property for, of course, a limited class of rings. And if you recall, this entire thing originated from that Fermat's last theorem, that in the proof of Fermat's last theorem used unique factorization implicitly, which broke down in that particular ring. But now that we have restored unique factorization, we can try going back to the proof and see how it works out. Unfortunately, that proof now breaks down. With that proof it doesn't work when you are using ideals. It only works when you are using numbers only. So, of course, then the attempts continue to prove Fermat's last theorem for another 100+ years. But what we got in place of proof was this notion of ideals. Now, they have certain utility in terms of what I just showed, but it has turned out that they have far more reaching utility than just this. So let's discuss that aspect of ideals. And for that, I'll again go back to the group theory we developed. We had this notion of subgroups in groups, and then we defined the notion of quotienting a group with a subgroup, which corresponded with a homomorphism between groups. Right? There is a nice correspondence between quotienting a group with a subgroup and the homomorphism from that group to another group. And we'll establish something very similar for rings. And we'll see that the ideals play the role of subgroups. So let's first work or define the notion of a homomorphism for rings. So the notion of homomorphism generalizes very naturally to rings. In groups, we have one operation, and homomorphism preserve that operation. In rings, we have two operations, so we want homomorphisms to preserve both the operations. So we say phi of A1 plus A2 is phi of A1 plus phi of A2, and phi of A1 times A2 is phi of A1 times phi of A2. All such mappings are homomorphisms. And further, if phi is a 1-1 on 2 map, then phi is an isomorphism. That's again exactly the same as for groups. And the notion of isomorphism allows us to deduce which rings are identical. If two rings are isomorphic, then essentially they are the same ring. Okay. Now, some properties of homomorphisms for rings. Firstly, you should expect that since it's preserved two operations, then it should satisfy more properties than the properties of homomorphisms for groups, and that is certainly true. For example, what is homomorphism of 0? If phi is a homomorphism, what is phi of 0? This is always 0. Why? Yeah, this follows because phi of 0 is phi of 0 plus 0, which is phi of 0 plus phi of 0. And then you can cancel one of them and then reduce phi of 0 is 0. Phi of 1 is 1. Second property, phi 1 of a1 dot a2 equals
Phi of 1 dot a1 and phi 1 dot a2 equal to phi of 1 dot a2. So phi of a2 equal to phi of 1 into phi of 1.
Okay, let's see that. What you're saying is that phi of 1 dot a is phi of 1 dot phi of a, and this implies phi of a times phi of 1 minus 1 is 0. Is this what you're saying?
So phi of 1 dot a is equal to phi of a.
Phi of 1 dot a is equal to phi of a, yes.
So we have phi of a on both sides.
Yes. So that's what I'm taking the right hand side to the left and writing that in this fashion. Now, does it imply that phi of 1 is 1?
Can be 0 1.
For integral domain, that's very right. If the ring is an integral domain, then one of them must be 0. So either phi of a is 0 for all a's. So that's a homomorphism. That's a trivial homomorphism. Every element is mapped to 0. Or phi of 1 is 1. Even if it is not an integral domain, if for any element a, it is mapped by phi to a unit of the ring R2, then also we can say that phi of 1 is 1. Recall the definition of a unit? Unit was an element which has an inverse within the ring. So for most of the rings, phi of 1 is 1. Rings and mappings, it's fine. So we will stick to this assumption that for homomorphism, phi of 1 is 1. So that just simplifies certain things. How about phi of a unit? What happens to this? When A is a unit of R1. Is phi of A also a unit of R2? Phi, we assume phi of 1 is 1, yes. Yes, why? AB is 1, yes. So phi of 1 is phi of AB. So 1 is which is phi of A times phi of B, and that shows that phi of A is also a unit. So that's a nice property which follows just by the fact that phi of A is 1 is 1. Now consider kernel, again exactly as defined as for groups. Consider all elements of the ring R1 which are sent to 0 by phi. This was same as same definition. And actually here we can define it in probably two different ways, since there are two units or two identity elements. Send phi of everything to 0 or send all those a's which are sent to 1. But defining it for 0 makes a lot more sense, as we will see. What can we say about kernel of phi? There, kernel of phi for groups was a subgroup. Here, it's an ideal. Why? See, phi of A1 plus A2 is phi of A1 plus phi of A2. If phi of A1 and phi of A2 both are 0, then that's all. Phi of A1 plus A2 is also 0. Phi of B times A is phi of B times phi of A. And if phi of A is 0, then this is phi of B times 0, which is 0. So that implies that the kernel is an ideal of the ring R1. And what does the kernel do? Or rather, what does the map phi do? It takes the ideal I or ideal kernel of phi within R1 and sends precisely that ideal to 0. Other elements it doesn't set to 0. So this is again defining that notion of quotienting in a very natural way. And again we can look at the equivalence classes that are created by phi within R1. Okay, and what are those equivalence classes like? Use the relation R, which is says that A and B are related if phi of A equals phi of B. And if you look at the set R, or you will have the equivalence classes. One would be the kernel. Okay, let's give a name to the kernel. Let I naught be kernel phi. Then there will be an I naught, one equivalence class. Other equivalence classes would be of the kind. Every equivalence class can be written in this form, that some C plus I naught, which means this has elements of the form C plus A whenever A is in I naught. And you can see that easily. Phi of C plus A is phi C plus phi A. Phi A is 0, so it's same as phi C. And whenever phi C is equal to phi D, then phi C minus D is 0. And therefore, these are precisely the equivalence classes one gets. Now, once you get these equivalence classes, let's again continue with our analogy with groups and try to define a quotient ring. If you recall, the quotient groups we define by taking these equivalence classes and defining a group operation on these equivalence classes. And we show that that's a quotient group. Can we do the same here? Okay. Let me stop here and leave this for the next class. You think it over. It's very natural. We can define the quotient class very easily. But I want you to give it some thought and we'll continue tomorrow.